We now move on with a topic that is rapidly transforming the future of cybersecurity, quantum computing. It's time now for the session, Quantum Computing and Cybersecurity. Please welcome Marta Pascual, CEO of Qilimanjaro Quantum Tech, and one of the leading voices in applying quantum technologies to real-world challenges. Warm round of applause, please.
Gracias. Thank you very much. Thank you for organizing this amazing event. Please don't run away. We're going to talk a little bit about quantum. I promise I will make it as approachable as possible. Quantum is hard. I admit that. Nobody understands it, not even me. So just bear with me, and we'll make sure that at least you understand the general concepts and why it's important. So we are a full-stack quantum computing company based in Barcelona. And what we are trying to solve is a very important problem. Maybe it's a problem that nowadays we don't realize yet, but it's about to come. It's already here. Computers have reached their limits. So we are very badly used to have a very rapid growth in progress in capacities of processing over the last years. We moved from having computers that occupied entire rooms to supercomputers that we can fit in a pocket in very few years. But this progress is not sustainable any much longer. We are reaching a limit. We cannot keep miniaturizing the chips as the same way we increase its power. And that's a problem, because at the same point, at the same time, we are living in a society that wants to be more and more and more digital every day, more connected. Now we are seeing the boom of artificial intelligence. Everything is about AI now. I use AI every day. And everybody is starting to use on a daily basis, also from the industry. That means a massive amount of data processing. That means a massive amount of model training and computing, the need of computing resources. Google, Meta, other large companies that need these resources, because they are offering these services, are building nuclear plants to power their data centers. This is nuts. This is crazy. We need to find a more sustainable way of doing computation. We cannot keep building these very large systems, because when we see the point that we cannot make them smaller, what we do is making them bigger, bigger, bigger. That's more expensive, not sustainable, and we will reach a limit very soon. Fortunately, quantum computing comes as a new hope to solve these limitations. And put in a very simple way, what a quantum computer does is to be able to encode data, information, into systems that behave under the laws of quantum mechanics. What is quantum mechanics? What we can see with the eyes, the macroscopic world, is described by classical mechanics, by Newtonian, by dynamics, by cinematics, and so on. It's the classical physics that we learned in school. But if we go to the microscopic level, to the things that we can see with the eye, we will see that atoms, molecules, and so on behave under some different phenomena, the laws of quantum mechanics. So it's under these laws that we can encode information, and out of this we can profit, we can exploit some phenomena that is very counterintuitive, such as superposition, being able to be in two states at the same time, entanglement and tunneling, that, put it very simply, allows you to build a new logic of manipulation of information. This new logic of computation allows you, for certain tasks, not all of them, to solve problems more efficiently. And what do I mean by efficiently? It's either faster, or with more precision, or in a more sustainable way, with less resources. This could have huge impact. And I'm not going to spend a lot of time here. It's just to make sure that you more or less understand the difference between the classical world and the quantum world. As you know, everything in information, everything in data is codified by bits. Everything, messages, images, everything that circulates that we use to communicate are strings of ones and zeros. This is the basic unit of information. In quantum, we have a different basic unit of information that is a qubit. And what's the powerfulness of the qubit? Is the fact that it can be in two, well, first of all, it's a quantum mechanical system, and it can be in two states or more. It can be in a superposition. So you don't have a 0 or 1 state. You can have a 0, a 1, or a 0 and a 1. And you can have different weights. And with this, what you can do is to parallelize your algorithms. You can, if you are doing a search algorithm, for instance, I always use the example of the maze, of the labyrinth, that you have to find the entry point and the out point. If you imagine this analogy, you have to go, in the classical algorithm, this is not precise, but just as an example, just bear with me. In a classical algorithm, you would go one by one, looking for all the options, as many trials as you need to go, unless you are lucky and you find it at the first time. With the quantum, with this capacity of having this superposition with the quantum bits, you can analyze all the possible solutions at once. That's an exponential speed up of your solution. And what are the applications? Because this doesn't come to kill the classical computers. We won't see quantum computers in our pockets, or at least I don't think so. This is an acceleration. This is an acceleration of computing for certain applications. And what are these applications? So I'm a chemist by training. I changed fields into physics and computer engineering, but originally I was working with drug design. I was developing new pharma to cure medicines that today, to cure diseases, sorry, that today do not have any cure. I was working with cancer, Parkinson, and Alzheimer. And the first step to do that is to simulate the molecules, to simulate the reactions that are associated to these diseases, to these harmful processes. And you do it with a supercomputer. But the problem is that these systems, these molecules, as mentioned before, they are described by quantum mechanics. And our computers do not have the same logic to describe them. So my frustration, and the reason why I changed fields, and the reason why I'm now leading a quantum computing company, was that it was taking way too much time and sometimes it wasn't even untreatable for me to get the results. And that sets a limitation of progress in research, in science, in developing new technologies, because we are not using the right tool for them. So there was this idea of using quantum mechanical systems to describe quantum mechanical systems, to use quantum computers to describe quantum nature. And this is for simulation of molecules, simulation of new materials, simulations of the world, of particle physics of the universe that surrounds us. And this will allow us to keep enhancing the knowledge of humanity, of nature, and the universe. And I think this is one of the most wonderful applications that quantum computing will bring to the world. But there are other applications that are very important. There's one type of problem that is all over the place in all the industries I've been talking to. Those are optimization problems, very simple problems. Distributing packages in a large city, optimizing a portfolio of financial assets to maximize benefit and reduce risk, or to optimize chirurgical rooms in a hospital. Those are problems that are on our very, very day-to-day, and are actually very complex. They have a complexity class in mathematics that are called NP-hard. This means that if the problem is small, if it has only a few variables, it's relatively easy to solve. But once the number of variables and the amount of data increases, and the number of constraints that we set to the problem increases, this becomes untreatable. It doesn't have an efficient solution with a classical computer. So the way to solve it is to use approximations. And the approximations affect the precision of the result. Luckily, these type of problems have a very common mathematical formalization that can be embedded into a quantum computer. Those are called Kubo problems. So optimization in energy, logistics, finance, sectors all over the world, all over the industry, can be mapped into a quantum computer to provide very important benefits and important margins in the precision they get on their results. And there's another one that I really liked, and we are putting a lot of focus on this one from Qilimanjaro. We are setting a completely new paradigm of computing. And now we see how AI models, machine learning, is changing our world. I mean, AI models and machine learning has been there forever. Now it's being translated into the day-to-day of the society, into production, if you like. But now we have the opportunity to completely reinvent AI. We have a new platform that allows us to think differently on how we do computation. And one of the issues that we have with AI nowadays, as I introduced in the beginning, is that they are very demanding in terms of computing resources. And one thing that we are seeing with quantum computing is that we can compress AI models, we can compress neural networks, but they are not neural networks anymore, it's something different. We can compress them into a quantum computer to use less resources and be more efficiently. Imagine merging these two powerful fields, quantum and AI, to build something completely new that is useful for society. And in the same way that I always like to put everything from a positive perspective, the constructive applications of quantum computing, there are destructive applications as well, and there's a threat. A powerful quantum computer can suppose a threat for society. We were talking about hackers, we were talking about cybersecurity, and that's something that puts this technology into a very strategic point of view from the governments and the different continents. So there's a very important geopolitical factor on the race of quantum computing. Quantum computing is becoming a race in the same way that the semiconductor industry or the space industry has been also a race. Because what's the problem? There's an algorithm, quantum computing algorithm, one of the first quantum computing algorithms that appeared. It has not been implemented yet, but it's been designed. That's called Shor's algorithm. And Shor's algorithm is a very nice algorithm that, in principle, you can think that it's not a threat. It's an algorithm that what solves is a factoring problem. Factoring problem is to go backwards into a multiplication. So you have the result, and you get the prime numbers that multiplied among themselves give rise to this result. But why is this a problem? Most of our data in the world is codified via RSA. And RSA is a cryptographic code that relies on factoring, because factoring with classical computers is hard to solve. But with a quantum computer, it's very easy. So imagine, once we have a quantum computer, all our data being disclosed. So that's why there's a lot of focus on making sure that there's sovereignty in this technology, that we understand it, because the worst thing that can happen to Europe or to any country is that the technology comes that is very complex and nobody knows how to use it. And quantum is hard. So it's very important that we put efforts in democratizing this technology. And also there's a lot of efforts on migrating cryptographic processes into what's called post-quantum cryptography. And I don't have a lot of time. I didn't weigh very well my slides, so I'm just going to be very quickly explaining what is the current status of quantum, because I want to send a message of calm. Quantum computing is not here yet. It will take some time. It really needs some development. We really need to scale up the technology. And this is a moment that it's very nice because it's very collaborative. So there are many startups like ours and research groups and universities and initiatives all over the world to bring this technology forward because of the revolutionary impact that we'll have with society. We have big technological giants investing also a lot of efforts from their teams, like Google or IBM, that are leading also this race from the US. But there are some complications because of errors. Most quantum computers out there, most of the prototypes that are being developed are called digital quantum computers. This is one of the most common paradigms. And the issue of digital quantum computers and quantum in general is that they are very sensitive to errors. And it's because of errors that we cannot make sense out of this computation yet. We can have some prototypes, we can make some proofs of concepts, but it's still not ready to put into production. And the only way to correct for these errors is through redundancy, like making the chips larger and larger and encoding logical units of information, encoding the qubits into many physical qubits, using redundancy. But quantum mechanics is a bit hard and demands for more redundancy than we would use with classical systems. So we really need to have chips that are of the size of millions and millions and millions of qubits to be able to correct for these errors. There's a lot of work and development towards this direction. Google is leading some of these initiatives, but we believe that you need to find alternatives as well, because At the moment, we are at the chip size of around 100,000 qubits, and if we need to reach millions, I don't want to wait that much time to see a quantum computer providing solutions. So that's why in Qilimanjaro, here in Barcelona, we're developing full-stack analog quantum computers. We learn from the history of technology. We learn from the history of computing. And one thing that we realized is that the first computers to provide value to the industry were app-specific. They were these big machines occupying entire rooms in the 1940s. They were app-specific, and they were analog, because they also had the issues about errors. Analog came first, then we moved to a digital world. Now we're going back a little bit to analog. So analog processing and digital processing have always been coexisting. And we think that analog processing in quantum will have a lot of benefits, because it bypasses the needs of error correction, it's more fault-tolerant to errors, and because we think that before you run, you need to walk. Before we are trying to reach universal quantum platforms, we need to find this killer application of quantum computing that surpasses classical machines. We really need to prove the quantum advantage for industry applications. We develop full stack. We develop quantum computers from A to Z. We provide the access. We develop the algorithms, the applications, the programming language, the operative system, because you have to reinvent everything. And we design and fabricate the chips as well. So we do everything. We like to do everything. Because at this stage, it's very difficult to externalize anything. So we are a startup that has to do all the supply chain, everything. And how do we democratize this technology? By providing access to it. It's still not ready to be put into production. It's still not going to solve some of the biggest, more complex problems in the world. But we need to make sure that people start understanding. We need to make sure that people speak quantum, because we cannot make this journey alone. We really need to develop the technology hand by hand with the end users, with the programmers, with the scientists, with the engineers, with everybody that is a user of supercomputers, in order to be able to direct the development towards the right use cases. And what are the use cases that we are exploring? So we are exploring all the industries, from logistics, last-mile delivery dispatching systems, to retail, warehouse optimization, very hard problems, aeronautics, drone routing, the energy, calculating the day-ahead price market. This is very related to the apagón that we saw the other day, the algorithms that distribute and understand the flows and the sources and the demand of energy in a certain market. Operating room resource optimization, this is a problem I didn't know, but actually it's a very hard problem. Commercial optimization in the telecoms industry as well, or green hydrogen production. Cybersecurity for critical infrastructure protection. This is something that was mentioned before. This is very relevant, such that we protect our critical infrastructure in the area of cybersecurity, of the threats of cybersecurity. And just to enclose, I want to show you a little bit what is a quantum computer. One of the quantum computers that we built, that we deploy, we have built already 6 quantum computers. We have commercialized some of them. And I just want to show you a little bit video to present that the quantum computer doesn't look yet like a normal computer. It looks like one of these huge computers that were occupying a room in the 1940s. And we hope that with the time, with the investment, with the support, we'll bring quantum computer to the day-to-day of all of us in the same way that AI is in the day-to-day of all of us now. Because without quantum computing, without a new way of doing computation that is more powerful, there's no future of AI. And there's no future of any new technology arising. And with this, I finish. Thank you very much.